Yeah, good morning students. So in the last class we have discussed about different TM modes, cutoff frequency, cutoff wavelength, phase velocity, group velocity, guided wavelength and expression for phase velocity and expression for group velocity, dominant mode and degenerate modes. So all these topics we have discussed in the last session, right? So TM modes. So depending on the values of M and N, so we have different modes in TM wave. So in TM wave we have different modes based on the M and N values. M and N values. Okay. So that is TM00 mode. So TM01, TM10, TM11, right? If M equal to 0 and N equal to 0, so if you substitute M equal to 0 and N equal to 0 in Ex, Ey, Hx and Hy equations, so all of the four equations will be 0, right? So that's why TM00 mode cannot exist. So if you substitute 0, 1 and 10 values also, so TM01 and TM10 cannot exist. Okay? So in TM waves there is no TM00, TM01 and TM10. Okay? So if you substitute M equal to 1 and N equal to 1, so then all four components will exist. So that's why TM11 mode can exist. TM11 mode can exist. And TM12 and TM21 and higher modes can exist in the TM wave. Okay? So that's the different modes in TM wave. So in TM wave we are having TM11 onwards. So what is the cutoff frequency? So cutoff frequency means the frequency at which the gamma just becomes 0. So that is defined as the cutoff frequency. So cutoff frequency, that is C by 2 into M by A whole square plus N by B whole square whole power 1 by 2. So there is a formula for the cutoff frequency. So the wavelength, if the wavelength is greater than or equal to lambda c, so that is attenuated, that wave is attenuated, and the wavelength is less than or equal to lambda c. The wavelength is less than or equal to lambda c, then that wave is propagated, right? So condition to propagate, the wavelength must be less than or equal to lambda c. Okay? And in the last class we have discussed about phase velocity and group velocity also. So the phase velocity is c by square root of 1 minus lambda naught by lambda c whole square, and the group velocity is so c into square root of 1 minus lambda naught by lambda c whole square, that is the group velocity. If you see the relation between phase velocity and group velocity, so Vp phase velocity into group velocity equal to c square, right? And see the relation between lambda naught, lambda g and lambda c, then you will get here it is lambda naught equal to lambda g equal to lambda naught by square root of 1 minus lambda naught by lambda c whole square. And what is the dominant mode and degenerate modes? Okay, the mode having the highest cutoff wavelength is known as the dominant mode. Dominant mode means the mode having the highest cutoff wavelength. The mode having the highest cutoff wavelength is known as dominant mode. That means it has a minimum cutoff frequency. Minimum cutoff frequency. What is degenerate mode? Some of the higher order modes having the same cutoff frequency are called degenerate modes. So the higher order modes are having the same cutoff frequency. Those modes are called degenerate modes. Right? So that is about dominant mode and degenerate modes. So now, today we will see the propagation of TE waves in rectangular waveguide. That is the TE mode analysis. Propagation of TE waves in rectangular waveguide. So the wave equation for a TE wave is, del square Hz equal to, this is del square Hz equal to minus omega square mu epsilon Hz. So we know that the wave equation for TE wave is del square Hz equal to minus omega square mu epsilon Hz. Here in the TE mode, Ez equal to 0, So the Z component of the magnetic field, so Hz must exist in order to have energy transmission in the guide. Okay, so here Hz not equal to 0. In the TE mode, the electric field is perpendicular to the direction of propagation, so Ez becomes 0. So Hz must exist, right? So that's why Hz not equal to 0 and Ez equal to 0. That is in the TE mode. So in TE mode, the wave equation is del square Hz equal to minus omega square mu epsilon Hz. So you remember this equation. So if you expand this equation, so you will get dou square Hz by dou x square plus dou square Hz by dou y square plus dou square Hz by dou z square. Okay. So just expand this del square Hz. So expand this equation, then we will get dou square Hz by dou x square plus dou square Hz by dou y square plus dou square Hz by dou z square equal to this one minus omega square mu epsilon Hz. Okay. So previously we have defined one operator, that is dou square by dou z square equal to gamma square. Dou square by dou z square equal to gamma square. So here in place of dou square by dou z square, substitute gamma square, right? Then it becomes dou square Hz by dou x square plus dou square Hz by dou y square plus gamma square, right? So we know that gamma square equal to dou square by dou z square. So in place of dou square by dou z square, so substitute gamma square. So it is gamma square Hz, this one gamma square Hz, and this omega square mu epsilon Hz equal to 0. Okay. So next, this we can write dou square Hz by dou x square plus dou square Hz by dou y square plus h square, this gamma square plus omega square mu epsilon. So take Hz is common, equal to 0. See here, in place of gamma square plus omega square mu epsilon, take h square. So in place of gamma square plus omega square mu epsilon, take h square. So it becomes dou square Hz by dou x square plus dou square Hz by dou y square plus h square Hz equal to 0. H square Hz equal to this one, h square Hz equal to 0.
రూపా నువ్వు చెప్పు. అవును రాము చెప్పింది నిజం. తను మహేశ్వరి అయితే బాబు ఎందుకు
అమృత. Okay, so the partial differential equation, so if you assume hz equal to xy, if you assume hz equal to xy, so where x is a function of x only and y is a pure function of y.
ఈ నాటకం ఆడుతుందేమో అనిపిస్తుంది. టైం తనకి అనుకూలంగా ఉన్నప్పుడు తన అసలు రూపం బయట
మా అమృత. Okay, thank you. Right? So from this equation, this one. So from the second equation, so we can write xy in place of xz. xy in place of xz.
ಇದನ್ನ ಅಷ್ಟೇ ಬಿಗ್ ಬಾಸ್ ಸ್ಟ್ರಾಂಗ್ ಇಟ್ಲತ್ತಲ್ಲ ಇಲ್ಲ ನೋಡ್ಕೆ ಕ್ಲಾಸ್
Ma Murta. Okay. Right? So in place of, see here, the second equation is dou square hz, right? Dou square hz by dou x square plus dou square hz by dou y square. So in place of hz, substitute xy. Right? So substitute xy. So here we will get dou square xy by dou x square plus dou square xy by dou y square plus h square xy equal to 0. So substitute hz equal to
ఇచ్చిది ఏం మాత్రం
from the second equation.
దానికి మనకంటే ఏదో ఉండి ఉంటుంది, అందుకే మనం బ్రతికిపోయాం. ముందా గబ్బరగాడిని వంటగది పక్కన గదిలో ఉన్న గార్బేజ్ కూడా.
Okay. So dividing this equation with xy on both sides. So dividing with xy on both sides, then you will get 1 by x dou square x by dou x square plus 1 by dou square y by dou y square plus h square equal to 0. So that is equation 3. Okay. So equating each item to a constant, then so we can write 1 by, see here, this one, 1 by x into dou square x by dou x square equal to minus b square, and 1 by y into dou square y by dou y square equal to minus a square. So substitute these two. So from equation 3, minus b square minus a square plus h square equal to 0, then we can write h square equal to a square plus b square, right? So it is up to this derivation is same as in the TM mode analysis. Okay, up to this the derivation is same, so as in the TM mode analysis. See here, so solving for x and y by separation of variables method, then you will get x equal to c1 cos bx plus c2 sin bx and y equal to c3 cos ay plus c4 sin ay. So if you substitute these two, then the complete solution is hz equal to, complete solution for hz equal to xy. So substitute x and y in hz equation, then hz equal to c1 cos bx plus c2 sin bx, c3 cos ay plus c4 sin ay. Here c1, c2, c3 and c4 are constants. Okay. Now we will see the boundary conditions. So if we check this equation in the TM mode analysis, the equation will be Ez equal to C1 cos Bx plus C2 sin Bx, C3 cos Ay plus C4 sin Ay. But in this TE mode analysis, it will be Hz equal to, okay, a simple difference. In TM mode, it will be Ez equal to, in TE mode, it will be Hz equal to. The remaining equation, this part is same for both TE mode and TM mode, right? So only the difference is, so in TM mode, here Ez equal to, right, C1 cos Bx plus C2 sin Bx and so on. But in this TE mode, it is Hz equal to C1 cos Bx plus C2 sin Bx and so on. Clear? So apply the boundary conditions. So for this equation, apply the boundary conditions. Since we consider a TE wave propagating along z direction, so Ez equal to 0. So we know that in TE wave Ez equal to 0, but we have the components along x and y directions. We have the components along x and y directions. Okay, so Ex equal to 0 along bottom and top walls of the waveguide, and Ey equal to 0 along the left and right side walls of the waveguide. So if we see the boundary conditions, see the first boundary condition, right? Check the first boundary condition. So you can check from TM mode analysis. You can check from TM mode analysis. So here Ex equal to 0. So see the bottom wall. See the bottom wall. So these boundary conditions we have explained in the TM mode analysis, right? So if you see the bottom wall, Ex equal to 0. So అక్కడ చూడండి y ఈక్వల్ టు 0 కనిపిస్తుంది, రైట్? సో అక్కడ మీకు ఒకసారి చెక్ చేసుకోండి, బౌండరీ కండిషన్స్ డయాగ్రామ్ చెక్ చేసుకున్నప్పుడు y ఈక్వల్ టు 0. ఓకే, సో x యాక్సిస్ మనం ఏం తీసుకున్నాం? సో x యాక్సిస్ మీద మీకు ఆ కండిషన్స్ చూడండి. సో అట్ y ఈక్వల్ టు 0, okay, at y equal to 0, x changes from 0 to a. X changes from 0 to a. Okay. So at y equal to 0, for all x tends to 0 to a. So like a third boundary condition ఒకసారి చెక్ చేసుకోండి. థర్డ్ బౌండరీ కండిషన్. సో థర్డ్ బౌండరీ కండిషన్ అంటే లెఫ్ట్ సైడ్ వాల్. సో మీరు లెఫ్ట్ సైడ్ వాల్ కనుక చెక్ చేస్తే Ey ఈక్వల్ టు 0. సో అక్కడ మీకు x ఈక్వల్ టు 0 తీసుకున్నాం. x ఈక్వల్ టు 0, రైట్? x ఈక్వల్ టు 0 తీసుకుంటే y చేంజెస్ ఫ్రమ్ 0 to b. Y changes from 0 to b. That is the left side wall, right? If you check the fourth boundary condition, Ey equal to 0. Ey equal to 0 at x equal to a. And y changes from 0 to b. That is the right side wall. Okay. So these are the boundary conditions. So substitute the first boundary condition. Substitute the first boundary condition. So in the equation 5. So we know that Ex equal to minus gamma by h square dou Ez by dou x minus j omega mu by h square dou hz by dou y, right? So we know this equation, Ex equation. Ex equal to minus gamma by h square dou Ez by dou x minus j omega mu by h square dou hz by dou y, right? So substitute the first boundary condition here. Since Ez equal to 0, the first term is 0. So we know that Ez equal to 0. Then substitute Ez equal to 0 in the equation 6. Then the first term becomes 0. Then Ex equal to, so remaining term, right? Ex equal to this one, minus j omega mu by h square. Ex equal to minus j omega mu by h square dou by dou y So here substitute Hz equation, right? So substitute Hz in equation 6. Substitute Hz in equation 6. So Hz equal to this one, C1 cos Bx plus C2 sin Bx, right? And C3 cos Ay plus C4 sin Ay. Substitute Hz equation in equation 6. Then you will get, so Ex equal to minus j omega mu by h square. Ex equal to minus j omega mu by h square. C1 cos Bx plus C2 sin Bx minus C3 a sin Ay plus a C4 cos Ay. Okay? A C4 cos Ay. So substitute first boundary condition here. So here Ex equal to 0, right? So substitute here Ex equal to 0. So 0 equal to minus j omega mu by h square. C1 cos Bx plus C2 sin Bx into a C4. Into a C4, right? Here C1 cos Bx plus C2 sin Bx not equal to 0. This one, C1 cos Bx plus C2 sin Bx not equal to 0 and a not equal to 0. Then C4 equal to 0. Then C4 equal to 0. So substitute C4 equation, substitute C4 in equation 5. Then the solution reduces to Hz equal to this one, C1 cos Bx plus C2 sin Bx into C3 cos Ay. Okay? So that is the first boundary condition. Next, see the third boundary condition. So from the third boundary condition, so we have Ez equal to 0 at x equal to 0 for all y changes from 0 to b. So third boundary condition means check the left side wall boundary conditions. So for this left side wall boundary conditions, at x equal to 0 for all y changes from 0 to b, and we know the Ey equation, and we know Vy equation. So Ey equal to minus gamma by h square. Ey equal to minus gamma by h square dou Ez by dou y plus j omega mu by h square dou Hz by dou x. So here Ez equal to 0, right? So Ez equal to 0 and substitute Hz. So then Ey becomes, so j omega mu by h square do minus b C1 sin Bx plus b C2 sin Bx into C3 cos Ay. Okay? So from the third boundary condition, Ey equal to 0, right? So substitute, so from the third boundary condition, substitute Ey equal to 0. So then you will get, so 0 equal to j omega mu by h square C3 cos Ay into b C2. Here cos Ay not equal to 0 and b not equal to 0 and C3 not equal to 0. So then C2 becomes 0. So only C2 equal to 0. Okay. So then this equation reduces to Hz equal to C1 C3 cos Bx cos Ay. Right? So that is the third boundary condition. Now apply the second boundary condition. If you apply the second boundary condition here, so the second boundary condition at y equal to b, for all x tends to 0 to a, the second boundary condition for y equal to b, the x changes from 0 to a. So and we know the equation Ex equation, that is Ex equal to minus gamma by h square dou Ez by dou x square. So dou Ez by dou x minus j omega mu by h square dou hz by dou y. Okay. So substitute the second boundary condition in this equation, then you will get here Ex equal to 0. So you will get 0 equal to j omega mu by h square. This C1 C3 a cos bx sin ab, right? So here cos bx not equal to 0 and C1 C3 not equal to 0 and sin ab equal to 0. So from this sin ab equal to 0 or ab equal to n pi. So we can write a equal to n pi by b. Okay. So if you substitute the fourth boundary condition, so in the fourth boundary condition Ey equal to 0 at x equal to 0 for all y changes from 0 to b. And we know the Ey equation, so it is minus gamma by h square dou Ez by dou y plus j omega mu by h square dou hz by dou x. Right? So substitute the fourth boundary condition and you will get the b equal to m pi by a. Okay. So this a value and b value is same as in the TM mode analysis. There also, so a equal to n pi by b, b equal to m pi by a, right? So substitute a and b values. So then you will get hz, the complete solution. hz equal to C1 C3 cos m pi by ax cos n pi by b y. So let C1 C3 equal to C, then we can write hz equal to C cos m pi by a into x cos n pi by b into y. So e power j omega t into e power minus gamma z, right? So here this z represents the wave is traveling along z direction and e power j omega t represents this is a sinusoidal representation, right? Okay, that is the hz equation. So it is the hz equation. So and we know the field components. So we know the field components. So Ex equal to minus gamma by h square dou Ez by dou x minus j omega mu by h square dou hz by dou y. Here Ez equal to 0, that's why the first term becomes 0 and substitute the hz in this equation and substitute hz. So what is hz? Hz equal to this one, c cos m pi by a into the cos n pi by by d power j omega t minus gamma z. That is the hz equation. Substitute this hz in this equation, in the Ex equation, right? So since Ez equal to 0, the first term becomes 0, then you will get Ex equal to this one, j omega mu by h square c n pi by by cos m pi by x sin n pi by by e power j omega t minus gamma z. So in Ex equation substitute Ez equal to 0 and hz equation, right? Then you will get Ex field component. Similarly, so take Ey equation and substitute Ez and hz and take hx equation and substitute hz and ez and hy equation, right? So finally we get the four field components Ex, Ey, hx, hy. Okay, so that is about propagation of TE waves in rectangular waveguide. So almost the derivation part process is same as in the TM mode analysis. Okay. So what are the different modes available in TE waves? different modes available in TE waves. So T is 0, first take T is 0, 0. Here, if M equal to 0 and N equal to 0, so substitute M equal to 0 and N equal to 0 in these four field components, Ex, Ey, Hx, Hy, right? So in these four field components, substitute M equal to 0 and N equal to 0. Okay, so it is the Ex equation, it is the Ey equation, it is the Hx equation, and this one is Hy equation. Substitute M equal to 0 and N equal to 0 in these four field components, Ex, Ey, Hx, Hy. Then you will get, so here the four field components become 0. So TE 0, 0 does not exist. In TM wave, TM 0, 0, TM 0, 1 and TM 1, 0 does not exist. But in TE, so only TE 0, 0 does not exist, right? So next mode is TE 0, 1, next TE 1, 0, TE 1, 1. So these modes will exist in the TE waves. Okay? So if you substitute M equal to 0 and N equal to 1, here if you substitute M equal to 0 and N equal to 1, so in these four field components, and M equal to 1 and N equal to 0 and M equal to 1 and N equal to 1, right? So all four field components exist. So TE01, TE10 and TE11 exist in TE waves. Okay. So these are the different modes, TE modes in rectangular waveguide. So next we will see the wave impedance of TM and TE waves in rectangular waveguides. So the wave impedance, to see the definition, the wave impedance is defined as the ratio of strength of electric field in one transverse direction to the strength of magnetic field along the other transverse direction. Okay, so the wave impedance here, the wave impedance along z direction, so it is ZZ equal to Ex by Hy. It is the ratio of strength of one electric field in one transverse direction to the strength of the magnetic field in another transverse direction, right? So from the definition we can write ZZ equal to Ex by Hy. Ex by Hy. So substitute Ex and Hy equations. For a TM wave, Hz equal to 0 and gamma equal to J beta. So substitute this Ex and Hy equations and this Hz equal to 0, all these conditions. So substitute in this equation, then you will get, so the wave impedance in TM mode is this one, eta into square root of 1 minus lambda naught by lambda c whole square, right? Here it is 377 ohms for air. So that is the wave impedance for TM mode. So if you see the wave impedance in TE mode, so similarly ZZ equal to Ex by Hy. So in TE wave substitute Ex and Hy. Here Ez equal to 0. So in TM mode Hz equal to 0, substitute Hz equal to 0, but in TE mode substitute Ez equal to 0 and gamma equal to J beta. So then you will get the wave impedance in TE mode, it is eta by square root of 1 minus lambda naught by lambda c whole square. Here it is in TM mode, it is eta into square root of 1 minus lambda naught by lambda c whole square. In TE mode it is eta by square root of 1 minus lambda naught by lambda c whole square. So that is the wave impedance in TE mode and TM modes. So with this I am going to stop the presentation. If you have any doubts, you can ask.